Okay, let's dive right into this. Welcome, everyone. Listen, if you're in class 10 and you're just completely tired of memorizing chemical formulas without actually understanding them, you are in exactly the right place today. We're going to crush Chapter 1, Chemical Reactions and Equations, and we're going to do it together. By the time we're done here, you are going to see chemistry not as some bunch of boring textbook rules, but as this invisible magic that is literally happening all around you every single day. We're going to lock this in so you never lose a mark on it again. You ready? Let's go. So, to kick things off, let me ask you a quick question. Have you ever wondered why a totally fresh slice of apple turns brown if you just leave it sitting on the counter? Or actually, here's a better one. Why do manufacturers sell you bags of chips that are like mostly filled with air? Spoiler alert, that is not actually normal air. The magical answer to both of these everyday mysteries lies entirely in chemical reactions. And by the end of this, you're going to know exactly what's happening. Here is our game plan for today. 1. Spotting reactions. 2. Balancing equations. 3. Combination and decomposition. 4. Displacements. And 5. Redox and real life. Let's conquer this. Section 1. Spotting a chemical reaction. So how do we actually know when a chemical reaction has taken place right in front of our eyes? I mean, it's not like the atoms are waving little flags at us, but they do leave clues. There are 4 major signs that basically scream, hey, a chemical reaction is happening. First up, a change in state, like 2 liquids mixing together to suddenly form a solid. Second, a change in color. Third is the evolution of a gas. Imagine dropping little zinc granules into some dilute sulfuric acid. Suddenly, you'd see water bubbles forming and bursting, releasing hydrogen gas. And fourth, a change in temperature. If a beaker suddenly gets super hot or cold all on its own, you know a reaction is going down. Okay, listen up, because this next part is a huge board exam alert. This is a massive, frequently asked question that examiners absolutely love to throw at you. If you take a magnesium ribbon, you're instructed to rub it with sandpaper to clean it before you burn it. But why? What exactly is hiding on that ribbon? Well, the answer is that oxygen in the air is super sneaky. It constantly reacts with the magnesium, and it coats it in this really thin, protective layer of magnesium oxide, or MgO. This layer literally prevents combustion. It totally stops the ribbon from burning, so you have to scrub off that MgO layer with your sandpaper. Once you do that and you light it up, it burns with this dazzling bright white flame and just turns into a white powder. Boom! Reaction complete. Moving on to Section 2, Balancing Equations Made Easy. Now that we know how to spot a reaction, let's step into the math side of chemistry. I know a lot of students get kind of scared here, but I promise you, balancing equations is really just like a fun puzzle. You just need to know the rules of the game. And the ultimate rule, which you probably remember from class 9, is the law of conservation of mass. Mass can neither be created nor destroyed in a chemical reaction. Basically, if you start with 10 grams of stuff, you absolutely must end with 10 grams of stuff. In chemistry terms, you gotta end with the exact same number of atoms for each element that you started with. No exceptions. To obey that law, we use what's called the hit-and-trial method. It's highly effective, and there are 3 foolproof steps. Step 1, draw a box around your chemical formulas, and whatever you do, do not change anything inside those boxes. You can only add numbers to the front. Step 2, pick the giant compound with the absolute most atoms to start balancing first. Make it easy on yourself. Step 3, balance the elements one by one across the left and the right sides. Just plug in numbers, check your counts, and adjust. Oh, and pro tip, use a pencil, not a pen, until you finally crack the puzzle. Section 3, Combination and Decomposition Reactions. I want you to frame these 2 reactions in your mind as exact opposites. Combination is making things, and decomposition is breaking things. But before we get into breaking them down, we really need to talk about temperature. Notice the contrast here. Exothermic reactions release heat. Just think exo like exit. The heat is leaving. Endothermic reactions absorb heat. You literally have to put energy in to make it happen. And here's a mind-blowing fact that examiners love. Human respiration is an exothermic reaction. When oxygen from your blood meets the glucose from your food, right there in your cells, it reacts, breaking down to give you carbon dioxide, water, and crucially, energy, which releases heat. Now let's look at a classic combination reaction, where 2 things combine into one. Take quicklime, which is calcium oxide. If you vigorously add water to it, it reacts heavily, releasing a ton of heat, so yep, it's exothermic, and it combines into a single product. Slaked lime, or calcium hydroxide. And this isn't just random lab science, guys. This is literally what is used for whitewashing walls in our homes.
The slake lime goes on the wall, then slowly reacts with carbon dioxide in the air to give the walls this really nice, shiny finish.
On the flip side, we have decomposition, which is breaking one compound into two or more separate parts. The compounds don't just break apart on their own, right? They need energy. So these reactions are endothermic. You generally have three triggers for this: thermal, which uses heat; electrolytic, which uses electricity; or photolytic, which uses sunlight. A really classic example for this: take white silver chloride and put it out in the sunlight. The light energy actually breaks it apart, and it turns into gray silver and chlorine gas. That exact photolytic reaction is the whole secret behind how traditional black and white photography works. Okay, I've got a golden memory shortcut for you right here for electrolytic decomposition. If you pass electricity through water to break it down, it obviously splits into hydrogen and oxygen gas. But the exam is going to ask you, why is one gas double the volume of the other? Well, think about it. Because water is literally H2O, 2 parts hydrogen, 1 part oxygen. So of course you collect the gas in a 2-to-1 ratio. Oh, and if they ask how you prove which gas is which, bring a burning candle near the test tube. Hydrogen is the one that will burn with a sharp, recognizable pop sound.
All right, section 4, displacements.
I want you to think of this one like a tag team wrestling ring, where the stronger, more reactive element just violently kicks out the weaker element from its compound. Let me give you some visual magic here. The iron nail trick. If you drop a shiny iron nail into a bright blue solution of copper sulfate, iron steps into the ring. Because iron is more reactive, it's tougher, it straight up kicks copper out of the solution. If you wait about 20 minutes, the bright blue of the copper sulfate slowly fades away, and the iron nail gets coated in this brownish layer of the displaced copper. Iron won the battle. Now, what if two compounds swap partners with each other? That's called a double displacement. And a lot of times this creates what we call a precipitate. Just commit this definition to memory. A precipitate is an insoluble solid substance that suddenly forms from mixing two liquids, and it just settles at the bottom. A massive board exam favorite is mixing lead nitrate and potassium iodide. They are both clear liquids, but the literal second you mix them, boom, a bright, insoluble yellow precipitate of lead iodide appears out of absolutely nowhere. It's like magic, but it's chemistry. And finally, section 5, redox and real life. This is where we bring together the trickiest reaction type of all, and we're going to see how it is secretly destroying things around you and sometimes actively trying to ruin your snacks. Let's get the definitions down first. Oxidation is simply the gain of oxygen or the loss of hydrogen. Reduction is the exact opposite, the loss of oxygen or the gain of hydrogen. And the ultimate memory trick to never mix these up? Redox is literally just reduction plus oxidation. They always happen at the exact same time. If one substance loses oxygen, the other substance has to gain it. They are absolute partners in crime.
And these redox reactions, they aren't just stuck in a lab somewhere. They're actively attacking our world. When metals are exposed to moisture and air over a long time, they undergo oxidation. We call this slow destruction process corrosion. It is the exact reason why iron gets covered in that flaky, brown rust. It's why your nice, shiny silver jewelry eventually develops a dull black coating. And it's why old copper vessels turn green. Literally billions of dollars are spent worldwide every single year just trying to replace iron that has been eaten away by oxidation. Which brings us right back to our opening mystery. We know why apples turn brown now. They oxidize. But wait, why do manufacturers fill your chips bags with nitrogen gas instead of just giving you normal free air from the room? I mean, what exactly are they trying to protect those chips from? To prevent transidity? Think about it. If they filled the bag with normal air, the oxygen in that air would immediately start reacting with the fats and the oils in your chips. The chips would undergo oxidation, which turns them stale, smelly, and completely ruins the taste. Nobody wants that. So they use nitrogen. Nitrogen is an unreactive gas. It basically acts as an invisible shield, stopping the oxidation process completely, so your snack stays perfectly fresh and crunchy. So the next time you open a bag of chips, you can thank chemistry for that crunch. And honestly, that's it. You have just completely mastered the core of chemical reactions. So I'll leave you with this final thought. What other invisible chemical reactions do you think are happening in your kitchen right now? Keep your eyes open and keep exploring.